Welcome everyone, welcome back. Hello to all those in class here. Yeah, so we are starting, I guess it's not really a new topic, but it is closely related to what we've been doing before in terms of using dimensional analysis to help turn our equations or our models into something that is more, let's say, mathematically amenable to approximating or solving these problems. And the focus of the last few classes has really been on creating ratios or comparisons, products or groups that we can kind of compare the numerator to the denominator of. So we create some dimensionless group, and we kind of see, based on the magnitude of that dimensionless group, kind of can we learn something about the physics or mechanics of our problem. So for instance, we talked last class about how the Weber number was used as a way to kind of test the hypothesis, perhaps, about the formation of phosphine in Venus's atmosphere. Alex, who joined and talked about kind of popping bubbles and wrinkling bubbles, used dimensionless groups to make an argument that surface tension was more important than gravity in the collapse of bubbles. This type of thing where we're making comparisons happens over and over and over again, and it's a really powerful tool for us if we can kind of reframe our models with terms that represent comparisons. And we kind of already did this when we looked at the projectile problem. So that's the problem of you throw a ball up in the air or you launch a rocket into outer space. And the question is you give it some initial velocity, how high is it going to go? And in that case, we kind of made a comparison in a bit of an ad hoc way where we said, well, you know, if I throw a ball up in the air, the ball's not going to go that high relative to the size of the Earth, and so therefore I can throw out this term. Our goal now is to kind of formalize that a little bit and allow us to come up with these dimensionless ratios and write our equations in such a way that we can actually use those dimensionless ratios to help us approximate the solutions. So this is something that is, to me, is strange that we are just teaching this now. You know, I kind of feel like dimensional analysis in its entirety is something that should be taught to undergraduates maybe in their sophomore year. And especially something like this, because when you read a scientific paper, you're going to often encounter dimensionless equations. And there is a lot of confusion, especially when you're getting started out, and especially when these equations are not trivial, about how they got there, what are the actual physical parameters, how do I go from, you know, something that I understand in terms of dimensions, like force equals mass times acceleration, to something that is a dimensionless form where you don't really know, you know, what are the actual physical parameters that I'm inserting into this equation. So I find it, to me, like, in a way, a bit of a disservice that I think many students, especially students pursuing their PhD, kind of learn this on their own in some sort of, like, through osmosis of reading enough papers. And so the goal of this lecture is to give you like a formal way of approaching this, so that way you can either non-dimensionalize your own equations, or starting with non-dimensional equations, you kind of understand how they got there, and maybe kind of go back and forth between the governing equations and what particular problem you're looking to solve. All right, so this thing. All right, so a lot of this class is based on using approximate methods, and approximate methods are often based on, often use comparisons to reduce complex problems to more straightforward ones. And so what we'd like to do is return to a problem that we're pretty familiar with, which is the projectile problem. And we'd like to come up with that small parameter that we talked about, that ratio of the height we're throwing this projectile up to compared to the size of the Earth. And we could do that in a more formal way, and in a way that you can use on kind of any equation you encounter. And the way this works, the way that we non-dimensionalize an equation is we're going to scale the variables in the equation using characteristic values. This is always the approach we're going to take. We talk a lot about these characteristic values, and I think oftentimes when people start dealing with non-dimensionalizing equations, there is this kind of discomfort in thinking like, well, what are the characteristic values? What am I supposed to, how am I going to scale these independent variables, these characteristic values? I don't even know what that means. And the good news is we're just going to introduce them as symbols for right now that are going to help our math. And then we'll come back at the end, and this is always the case, often the case, we'll come back at the end and determine what those characteristic values are. Sometimes you know them. Sometimes you determine them experimentally. Sometimes you kind of know them because if you're working on some sort of canonical or classic problem, they often end up having the same form. Like diffusion problems often have a characteristic timescale that is pretty familiar to people. It's like some sort of length squared over the diffusion constant. But you don't need to know them. And if you don't know them, what we'll do is we'll just introduce them, these two constant values, and we'll figure out how to determine them. So let's go back to this projectile problem. And if you recall, the projectile problem deals with the acceleration, the second time derivative of x, which x is the vertical height of your projectile. And this is equal to negative gr squared over r plus x squared. R here is the radius of the Earth, g is the acceleration due to gravity on Earth, x is the height of the ball, and the over dot represents a time derivative, so 2 over dots, it represents the second derivative of the circuit time. And what we're going to do is introduce two constant characteristic values. And we're going to call them characteristic height, which we'll call xc for characteristic, and the characteristic time. I should be more careful here because this is it's really just the variables in our problem here, so it's not just the independent ones. The dependent variable x is also what we're dealing with. So, sorry. Let's pretend like I never did that. Okay, and the way this works is we use we're going to substitute and create new variables for x and t using these characteristic values. So what does that mean? That means what we'll do is we'll come over here and say that I'd like to let x be equal to xc times a new variable u. So and then I'm going to do the same thing for t. So I'm going to say my time is going to be replaced with my characteristic time times a new variable s. I'm going to be extremely clear here. X has a length scale. It's a scale variable, has a scale of length. The characteristic length also has a length scale, characteristic length, and therefore U is dimensionless. Same thing with time. Time is seconds or some measure of time. Your characteristic time is also has units of time or seconds. S is also dimensionless. So okay. And so the procedure here is pretty straightforward. So this is always what you're going to do. You're going to identify the variables in your problem, independent and dependent variables. You're going to create characteristic values for each of those variables. And then you're going to replace those variables with your characteristic value times some dimensionless variable that represents, in this case, U represents our height, dimensionless height, and S represents our dimensionless time. So it's not quite as straightforward as just inserting these. Into here. And the reason for that is because in order to insert those into there, we have to recognize that we are taking derivatives of our variables. And so in order to take derivatives of our variables, we also need to take derivatives of our new variables. And so we need to recall the chain rule. So I'll put that over here. I'm going to do this one out, but we'll do another problem, I think, in this class today, where I'll have you go through this on your own. So we have to take a second derivative of space with respect to time. It's easier to see if we start with the first derivative. So the first derivative would be something like d by dt. And from the chain rule, we can break down our derivative of our new variable as ds by dt times d by ds. Because now we're going to want to be taking derivatives with respect to s instead of taking derivatives with respect to time, because s is our new time variable. So we'll do that. That means, okay, well, ds by dt. So let's take a second here. S is equal to t over tc. Therefore, ds by dt is simply equal to 1 over tc. Move that out of the way. And so therefore, I can write this first derivative as 1 over tc times d by ds. Not too bad. Although we actually need the second derivative. We'll need that first derivative for our initial conditions, but for right now, we have to recall that we also need the second derivative. Second derivative looks like this. d by dt. I'm just kind of being quite pedantic here, but second derivative is going to look very similar. You can go through this whole process again. We're going to multiply the derivative by the second derivative. And we're going to end up with 1 over tc squared times the second derivative. I just so I'm being clear here, I'm treating, and I think this is a healthy way to think about these objects going forward. I'm treating this as an operator, you know. Here and here. This is an operator. This thing is saying, like, I need to operate on a variable, and I'm going to take a second derivative of my variable. And so I haven't written what I'm taking a derivative of here. I've kind of like separated out the derivative operator from the thing I'm taking the derivative of. So this is just like d by dt of something. If I want to do d by dt, I actually should replace it with 1 over the characteristic times d by ds. So we'll keep coming back to this idea of treating these as operators that operate on variables. So in that case, okay, let's go back over here. So on the left-hand side, we have a second derivative. Let's kind of come down. And so I can substitute this stuff in. So if I want to do that, I say the result of this, so my second derivative now becomes 1 over TC squared times my second derivative with respect to my dimensionless time now. Now I need to actually tell it what this derivative is operating on. Well, it's going to operate on x. We're no longer using x, we're now using xc times u, so this becomes xc.
Professor?
Yep.
I'm not sure if I'm just doing this wrong in my head, but is that supposed to be -1 over TC squared?
I don't think so. So if I go back over here, so d by dt is equal to ds by dt times d by ds. And s is equal to t over tc. So if I take the derivative of s with respect to t, I should just get 1 over tc. And then this second derivative is like the derivative of the derivative. And so if I'm taking this, I believe it should keep the same sign. Yeah, I think it's correct. This should still just be a positive 1 over tc squared.
Okay.
Yeah, that's not really a clear answer, but I think this is. I'm sure this is correct. We're really just kind of taking this derivative. Like we're kind of taking the derivative twice, and so you're kind of like multiple. You're essentially taking this times itself, which is square it.
So are we taking the, sorry, I'm just a little confused. Are we taking derivative of t or tc?
Of t, we're taking the derivative of s with respect to t.
Okay, so we're treating tc as a constant.
TC, yeah, and that's actually absolutely okay. So hold on, let me make that extremely clear. These are constants.
Okay, okay, that makes sense then.
Yeah, these are constants, and they are always constants. The characteristic values that you insert are always a constant value.
Okay, thank you.
Okay, coming back over here, we just got to deal with the right-hand side of the equation. So our negative sign still lives there. Our numerator stays unchanged. And then our denominator just becomes r plus xcu squared. Okay, so now we have removed all of our original variables from our problem. We only have dimensionless variables. And we have introduced these characteristic time and length scales that we don't know what they are. Now our goal is to collect the parameters in this equation into dimensionless groups. So recall the parameters in our equation are things like g, u, xc, tc, and we want to collect them into dimensionless groups. This is going to be the way that we create these ratios and comparisons that we're going to use to simplify and approximate our equations going forward. Unfortunately, there's no unique way to collect these parameters into dimensionless groups. So for example, I could take the right-hand side of this equation and I can factor the denominator in 2 different ways. So I'm going to take the denominator here. Actually, I'm going to draw this a little differently. I could factor this denominator to look like this. I could pull out, so I have r squared as 1 plus xc u divided by r. squared. Take a minute just to verify in your head that I'm factoring out the r squared. Or, instead of pulling out the r squared, I could pull out the characteristic length scale xc. So in that case, I would get something like this. That's an awful r. Just to verify and make sure that we're being sane here, u is dimensionless. We already said that. R is a length, xc is a length, so this is dimensionless. And I have a length squared out front. And likewise over here, dimensionless. Length over length, that gives me dimensionless. One's obviously dimensionless, and I pulled out a length squared. These are just two ways that we could factor the denominator here. And there's no kind of clear way of saying which one's right or wrong. There's not really a right or wrong to be had here. This can cause a lot of confusion, and it also means you kind of have to play and rearrange things in the way that simplifies the equation to your liking or to into a manner that's kind of convenient for you to work with. So in this particular case, this ends up being the more useful factorization for us. Anyone guess why?
The r squared cancels out.
Yeah, exactly. It allows us to cancel out the r squared in the numerator. It's as simple as that. And so sometimes it's obvious, or I don't know about obvious, but at least like you can kind of deduce why one might be useful. And sometimes it's not. You kind of have to play and then realize like, I kind of wish I had this written in a different way. So I wish there was a way that I could make that more straightforward, but it's just, this is a little bit more of an art than a science. Okay, so coming back over here. So we're going to use that one on the left that I boxed in yellow. And I'm going to pull out. So if this quantity is a constant, as we said, then we can pull it out of the derivative, right? So we can move this thing over here. And I'm going to use this in my denominator, which will let me cancel out the r squared with this r squared. So doing a little bit of algebra and recognizing what's a constant and what's not. Oh, the other thing I'm going to do, sorry, is I'm going to pull gravity. Oh, where'd it go? Pull gravity to the other side of the equation. And I'll tell you why in just a second. Remember, our goal here is to create dimensionless groups. So I'm going to have xc in the numerator. I pulled that out of the derivative. Divided by g, I moved it over from the right-hand side of the equation. Tc squared times my second derivative of u with respect to s. You could write this as u double dot. I'm choosing not to, just so that there's no ambiguity, because I said at the outset of this lecture that the double dot notation was the second derivative with respect to time, and so just so that we're not pretending or thinking that that's with time, I'm just leaving it as a second derivative here. All right, that equals negative 1 plus xc over r times u, and that's all squared. So the reason I pulled the gravity over to the left-hand side of the equation should probably be more clear now, because this quantity, length over time squared, is an acceleration divided by an acceleration. That's dimensionless, and this thing was already dimensionless. We already talked about that. And so now I have my governing equation entirely in dimensionless form. Dimensionless, 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 dimensionless. Everything's dimensionless here. We can do the same for our initial conditions, which I realize now I didn't write down before. But our initial conditions are such that the height at time 0 is 0. That's pretty straightforward. I'm basically not saying my dimensionless height is still 0. Nothing changes there. My second one is my acceleration, so I would have to apply the chain rule that I discussed earlier, and saying that the derivative of u at time 0 with respect to s is equal to my characteristic time over my characteristic length. Xc comes from the fact that we substituted in for x here, xc times u, so I just moved it from the left-hand side to the right-hand side. And tc comes from the fact that I took a derivative with respect to s, so I moved it from the left-hand side to the right-hand side. This is a velocity, this is 1 over velocity, and so we're dimensionless. Okay, so we have now rewritten our differential equation, our system a differential equation with its initial conditions in entirely a dimensionless form. And we've identified 3 dimensionless products or dimensionless groups. So let me highlight those. So we'll call this thing capital Pi 1. This will be capital Pi 2. And this is capital Pi 3. And just to kind of make sure that we're all on the same page here, you might say, oh, the equation is dimensionless. Why are we doing any more work? Like, isn't this what we accomplished? We wanted to get a non-dimensional equation. Yes, but it's dimensionless, except we have no idea what xc and tc are. So before, we can't really be done until we actually figure out or determine what the characteristic length and time scales of our problem are.
Shouldn't pi 3 be all of it?
Yes, it should be all of it. Thank you. Circled. Yeah, perfect. That actually brings me to the point I wanted to make. Thanks for pointing that out. Which is that these dimensionless groups do not involve the variables in our problem. Okay? So they do not involve u or s. They're only including the parameters, x, c, tc, g, r, and initial velocity. So I'm going to write these things down, actually. Ah. That's terrible. So for one, they don't involve variables, they only involve parameters. Number 2, they're dimensionless, and we accomplish this by just rearranging the equation and grouping terms together. So there is a little bit of work that needs to be done on your part. This part should be obvious from the definition. But this part, I think, is the part that can trip people up, is the fact that we have to accomplish this by rearranging our equations. And 3, and this one is really important, and it's a little bit more subtle. It is that they are independent. And that means it's not possible to write one of them in terms of the other, another or another two. Here I'm using subscripts, saying it's not possible to write, for instance, pi I in terms of pi j or pi k. You'll find this, not in this problem, this one is sort of clear, but I think on the midterm problem, one of the most common mistakes you'll make is when they get to their dimensionless groups, they don't recognize that, like, oh, I have 7 dimensionless groups, but actually pi 5 is 1 over pi 2. That's not independent, so you only need one of those. Or even worse than that is, like, actually pi 4 is pi 3 times pi 6. And in that case, those are not independent either. So what you're looking for are independent dimensionless groups. You can't write pi 1 here in terms of pi 2 or some product of pi 2 and pi 3. So that's the first part. Now the second part is we can already, before we do anything else, and before we even know what the characteristic values in our problem are, we can look at these and kind of glean some physical insight from them. So pi 1 is clearly the characteristic acceleration of our projectile relative to the Earth's acceleration due to gravity. So you can kind of already guess that if the acceleration of your projectile, or if the xc over tc squared is much larger than g, then gravity is not going to have much of an impact on kind of pulling this projectile back down. So you kind of already see the value in having these comparisons, even if you don't know exactly what the characteristic acceleration is. Pi 2 is the one that's familiar to us. Oh, yeah.
Sorry, I have a quick question. This might not be a smart question, but you said specifically it can't be written as a combination of 2, but what if you have like 7 and there's some way of doing it where 3 are combined? Like, is that under the same rule or?
Same rule. So you would basically, if you can write one of them as a combination of others, then that is not actually a dimensionless group.
Okay.
You would just rearrange your equation, or simply just leave it out and say that I don't need, for instance, pi 7 because it's just a combination of the other two. And so, yeah, that's always true. They have to be independent, and if you do derive more than needed, then you'll just essentially neglect the others because they're not going to enter the problem. Yep, question in class.
Thank you.
So is there a rule regarding like the number of dimensionless terms we're looking for, or previously it was kind of like the number of variables we're looking at, and we look at the number of fundamental mass, like the difference between those two?
Yeah, I think you can, just like we did with the Buckingham Pi theorem, and you can use the Buckingham Pi theorem to kind of say, all right, how many independent dimensions do I have? How many parameters do I have? Therefore, I should be able to take the difference between those two and determine how many dimensionless groups I should expect.
Okay.
I was thinking about it, but how can you use Buckingham Pi theory in basic logic? Because it's kind of vague for me, because we have x to dot as the thing we want to determine, and we have z, r, and x, and we also have m and l and t. So it says, it implies that we don't have any dimensionless group.
Well, I don't know. So the question is kind of, it seems like Buckingham Pi would not predict we would have these 3 dimensionless groups. It's not obvious to me. Let me do one thing really quickly, which is to say, we have to consider the whole problem. And in order to do that, I should have written x at 0 0. So I don't actually know. I've never really tried to construct this problem from Buckingham Pi, but I think here's what I think is going to happen. It seems like we have two. I think what you're getting at is it seems like we have too many dimensionless groups, and the answer is we do, because we haven't identified the characteristic values yet. And I think once we identify the characteristic values, what you'll see is that we're going to be left with only one dimensionless group, which I think does work out of Buckingham Pi. So right now we have too many, but that's because we don't know what TC and XC are. And I think once we complete the problem, we should have the right number, and it'll, I think, be more clear in that way. And that's basically what we had when we first did this problem, where we basically said the initial velocity, so the height of the projectile should be determined by some ratio of kind of the initial velocity and gravity, and basically v squared over g or something. And we said pi 2 here was really small. So that's kind of like saying, okay, my x is going to be equal to something that gives me a length scale times some unknown function of a dimensionless group. And we said, well, x over r is really small, so let's throw it out and just say that our x depends on only the kind of dimensional ratio that results from kind of balancing the dimensions. So I think once we go through, you'll see that it shakes out to what you would see from Buckingham Pi. So we talked about pi 1, we talked about pi 2. Pi 2 is the one that's familiar to us, how high is the ball relative to the Earth's radius. And pi 3 is a measure of the typical characteristic velocity relative to its initial velocity. So those are the physical concepts that we can glean from looking at these dimensionless groups, although we still don't know what they are. So how do we determine the characteristic values? And that's where we'll go next. There's basically this process is not trivial. There's a bunch of ways you can do this, but there is a process that we can follow that I'll go through in this class that'll make it at least a procedure that you can kind of lean on. So we have two characteristic values that we want to determine, XC and TC. And in order to do that, what we're going to need to do is set two of the dimensionless groups equal to 1. We want to find out, we have two unknowns, we want to set two of the dimensionless groups equal to 1. What does that mean physically, to set a dimensionless group equal to 1? Physically, what it means is that ratio or that comparison cannot be neglected. The order of the kind of numerator is on the order of the denominator, and so therefore we can't throw it out. It's very important to this problem. There's nothing kind of small or too large about it that will allow us to neglect it. It's usually, and it kind of makes sense, if it's really important, it should help us determine the characteristic or kind of important values of our problem. And that leads directly to the first rule. And this should also kind of make sense based on this idea that what we're saying is that the dimensionless group is so important that we need to retain it no matter what we choose for our characteristic values. And so rule 1 says, well, any of the dimensionless groups that appear in the initial or boundary conditions are so vital that we need to keep them in the problem. And the way we keep them in the problem, this is the confusing part, the way we keep them in the problem is by assigning the magnitude of that dimensionless group equal to 1. It's not small, it's not large, it's kind of the order of the problem that we want. So rule 1 says set pi I, this could be more than 1, there's only 1 here, but in other problems it can be more. Set pi I in the initial conditions or boundary conditions equal to 1. I'm going to repeat myself. You can apply this rule more than one time if there are more than one dimensionless groups that apply in the initial or boundary conditions. In this case, there are not, so we're only going to apply it once. Rule 2 is less straightforward. And this one says, set the dimensionless groups that appear in the reduced problem. Okay, this one's a little bit more tricky. And what this one means is, imagine that one of your dimensionless groups is small or large, or that you kind of know that in some limit it could be neglected. And the reduced problem is the equation that results if you were to throw out that dimensionless group. So here, we'll go through this in a minute to make it more clear. So first, let's apply this first rule here, and then I'll kind of walk us through the second one. This first one's pretty straightforward. It says take the pi that appears in the initial boundary conditions, set equal to 1. Well, pi 3 appears in the initial boundary conditions. Pi 3 equals TC over XC times V naught, set equal to 1. And then we can choose to solve for one of these variables. So we don't have enough equations, so I'm just going to pick XC just because it's simpler than saying that. Oops. XC, therefore, is equal to the initial velocity times TC. Doesn't help us yet because we still don't know what TC is, but we'll come back to it. Okay. Now let's go to the second rule. So the second rule says pick the pi that appears in the reduced problem. So let's look at our equation. So if I just replace all the variables with our pi groups, I would say pi 1 is equal to the second derivative of u with respect to s, and that's equal to negative 1 over 1 plus pi 2 times u squared. So we have two options here. We already set pi 3 equal to 1. So pi 3 we don't even have to worry about anymore. We either have to set pi 1 or pi 2 equal to 1. And this rule says pick the one that appears in the reduced problem. Well, the reduced problem here is the one in which we throw away this small parameter and we solve just the second derivative of acceleration is equal to negative 1. Or in the case of what we did in the last class, it would be equal to negative g, and we integrate twice, and we solve for the height of the ball. If we throw out the pi 1, then we don't really have a differential equation anymore. What are we even solving for? We don't really have the ability to apply the initial conditions, which we said are really important. So we can't throw out pi 1. Pi 1 has to stay. And so rule 2 says pick the pi that appears in the reduced problem and set it equal to 1. So pi 1 appears in the reduced problem because we're going to throw out pi 2. Can't really throw out pi 1. And so we're going to then, and this is the part that I think trips people up, we're going to take pi 1 and set it equal to 1. So pi 1 is xcg tc squared.
Were you setting pi 2 equal to 0 or to 1?
In the reduced problem, I'm setting it equal to 0.
Okay, so
This is for the reduced
So
problem, to be clear.
by reduction, pi 1 is equal to 1, not that we're necessarily setting pi 1 equal to 1.
Well, not quite, because well, this equation says that pi 1 times the second derivative of u, which we don't know, is equal to -1.
Yeah. Okay.
So the product of pi 1 times the second derivative of u is equal to -1, but we don't actually know what it is. So this is why we're basically gonna say we need that value, we need that dimensionless group to remain. It's always going to be of dominant order, and so we're going to set that equal to 1. And so let's see here. So if we set that equal to 1, we get xc is equal to v0 squared
Professor.
over g.
So sorry, do you mind re-explaining why we're throwing out pi 2 and not pi 1? I still don't understand when you say like pi 1 is like the dominant one.
So if we think back to what we're solving, we're saying the second derivative of the height of the ball with respect to time is equal to this stuff over here. So some combination of gravity, the radius of Earth, and it's nonlinear because of the appearance of this squared x term on the right-hand side of the equation. And so we ended up with, if I just look over here, retaking this equation here where I've got pi 1 and pi 2. I'm just rewriting that equation in terms of pi 1 and pi 2, and that's here. So the question is, what is really important, or what is a limit that we could take that would reduce the problem in complexity to something fairly trivial? So the simplest way to reduce this problem to a straightforward differential equation that we could solve is to get rid of the nonlinear term. It's to get rid of this term down here, this u squared. This is my nonlinear term. So if I get rid of that, this just equals -1. That's the problem we solved on day 1 in this class, is we solved the projectile problem here. Now look what happens if I choose to say get rid of pi 1. If I choose to get rid of pi 1, I don't have a differential equation anymore. And we've already said kind of the most important part is ensuring that the initial conditions of this problem are going to dictate the height of the ball. So the initial velocity is so important. It's in the initial conditions. It is going to dictate the height of the ball. If we throw out and set pi 1 here equal to 0, this entire term goes away. We don't have a differential equation anymore, and therefore there's no way to apply the initial conditions. So in this case, there's kind of 2 rationale that we could use to throw out pi 2. One is throwing out pi 2 gets rid of the nonlinear term. And this is often the way that people think about the reduced problem. Is like, and we're going to do this again next. We're going to deal with the diffusion problem, but we're going to look at a slightly different diffusion problem that makes it nonlinear. In that case, your head should be thinking, well, this equation is really awful. The diffusion equation is simpler. Why don't I throw out the thing that makes it awful and reduce it to the diffusion equation? Same thing here. This term is nonlinear. That makes it hard to solve. Perhaps we could still learn quite a bit about the height of this projectile if we just ignore that nonlinear term. So that's one of the rationales you could use to throw out pi 2. The other is If you throw out pi1, you don't have a differential equation anymore. You can't apply your initial conditions. Your initial velocity doesn't enter the problem at all if you can't apply your initial conditions. And so you're not even really throwing a projectile up anymore. So that would kind of imply that you should really keep this term. So throw out whatever else you can so that way this term remains. Does that help?
Yeah, that helps a lot. Thank you.
Yeah, another question
Yeah,
here.
so just to be clear, so how many pi terms are we throwing out to get to the reduced one? We getting it so it's just one pi term that's left, or yeah?
We are, I would say think of it a different way. There are two unknown characteristic values that we're trying to solve.
Yeah.
In order to find them, we have to find two pi groups to set equal to 1.
Okay.
So instead of thinking about what we're throwing out, think about it as we need to find two pi groups because we have two characteristic values. And it's what are we going to choose to set equal to 1.
Got it. Thank you.
Okay. We're almost done.
Would it,
Yeah.
sorry.
No, it's
maybe,
fine.
maybe we're going backwards with this question, but would it be valid to do it the other way around, where you do pi1 is equal to, oh, never mind, that's essentially equal. Never mind.
That's fine. No, think it through. That's totally fine. Okay. I guess I probably should have solved for TC in this top one, but whatever, it doesn't matter. Well, now that I know XC, I can solve for TC and find that my characteristic time scale is set by my initial velocity over gravity. And so now, just by non-dimensionalizing our equations, collecting them into dimensionless groups, and then kind of using our physical intuition to determine what is essential to our problem. The initial boundary conditions are always essential to your problem. The second part, finding the reduced problem, is a little bit more tricky, but hopefully it makes more sense now. But by identifying what is essential to the problem you're trying to solve, you can determine what the characteristic time scale and characteristic length scale in your problem are. Characteristic time scale is a ratio of the velocity to gravitational acceleration, and the characteristic length scale is the ratio of the velocity squared to gravity. All right.
Can I ask a quick question about how did you get between the XC equals V naught TC and then TC equals V naught over G?
Sure, I just took, that's why I was saying I kind of solved this backwards to make life a little bit more tricky for you. I took XC here and put it, oh, that's off, we can't read that. I took XC here and put it in here, and then solved for TC.
Okay. Then I guess my question is, how did you get XC equals V naught squared over G from the XC over G times TC squared? Did you do the same thing where you plugged in the one before it?
Yeah, you basically have two equations and two unknowns. And so
Okay.
just solving, yeah, exactly. Just solving that system of equations, you can identify the characteristic length and time scales, because you have essentially, I kind of did it piecewise, which is a little bit messy because you have to kind of go back and forth, but it's two equations, this one and this one, two unknowns, and you can kind of solve for it how you like it. Okay, so now we can kind of wrap up, and we can kind of go back and write down our dimensionless equation. And our dimensionless equation becomes the second derivative of u with respect to s, which is our dimensionless space and time variables, is equal to -1 v Oh, it's awful. I'm gonna make this bigger. Sorry. Try that again. Font. There we go. And our initial conditions, we already wrote those down. Those write down again. Clarity. So now our new problem becomes this, and this quantity here that I've written in my parentheses, this is pi 2. And you'll notice that it's a little bit different than what we had initially identified, which is like the height of the ball relative to the radius of Earth. What this is saying is that this pi 2 is really the characteristic height of the ball relative to the radius of the Earth. Subtle, but different. We found it in a more formal way. We didn't need to know anything. We did need to know that we chose to reduce the problem's complexity by getting rid of the nonlinear term. And this term down here is the nonlinear term. Or this term, this term actually. But the other thing we know is that if we are able to reduce this problem by saying pi 2 is small enough that in principle we can neglect it, then pi 2 is a small parameter. And this is going to be really, really important. So we will often say pi 2, in this case, is a small parameter. And we're going to introduce a new variable that's going to represent our small parameter kind of from this point on. And that is, we're going to call epsilon our small parameter. I should be clear. What I'm saying here is not that epsilon is always pi 2, it's that epsilon is a small parameter. So there's two things we need to do. So first, let me just write out our equation with our small parameter in there, just for clarity's sake. So here's our dimensionless equation of the projectile problem, written in terms of dimensionless space, time variable, and with the introduction of a dimensionless ratio, epsilon, which we're saying is a small parameter. The consequence of there being a small dimensionless parameter is the subject of the second portion of this class, where we talk about approximate methods and pertination analysis. Well, what we do is we typically look for solutions by saying, well, if we have a small parameter, what if we assume the small parameter is 0? Okay, well, maybe we can approximate our solution even better if we bring that small parameter back and we add it in just a little bit, we solve it again. We can kind of essentially use approximate methods in which we increase the importance of epsilon, our small parameter. There's some mathematical methods that we're going to discuss. So the fact that we've identified a small dimensionless parameter in our problem is really, really important because it enables us to use a bunch of mathematical tools that will allow us to approximate this. So if you recall in the projectile problem, basically what we said is we solved it, and you solve this in like, you know, first year physics or high school physics, where you fill a ball up and you say the nonlinearity due to gravity is small, how high is the ball going to go? When you solve this equation, it's a very straightforward ODE to solve. Now we're saying, because we have this small parameter in there, we we can use advanced mathematical techniques to kind of probe and understand exactly what that nonlinear term is doing. And not in a qualitative way like we did before, where we said, oh, well, if gravity, we're assuming it's uniform, but it's actually non-uniform. And when I throw the ball up, I would expect that if I throw it really, really high, Earth's gravity should have less of an effect on it, and it should go higher than I would expect. Now we can actually quantify that by introducing this parameter here. Now we can actually say, okay, well, now I know exactly how high this ball will go by including the nonlinear effects of gravity, to the point where I can define important parameters like, for instance, the escape velocity. How fast do I need to throw this thing up so that it actually leaves Earth's atmosphere? That's all well and good, but we should probably check that all the assumptions we made in deriving this equation are accurate, and that epsilon is actually a small parameter. So is epsilon small? Well, what's epsilon? Epsilon is v naught squared over gr. So r is the radius of Earth. I found it to be 6.4 times 10 to the 6 meters, roughly. G is like 10, say 9.81 meters per second squared. Putting this together, epsilon is approximately 1.6 times 10 to the negative 8 times my initial velocity squared. So for most projectiles, epsilon is small, and that confirms what we hoped to find, that this was in fact the right way to dimensionalize it, and that it was reasonable to say the reduced problem would involve throwing it out because it's probably small. Questions?
I do have a question. So just kind of going back, we originally had 3 pi groups, right?
Mhm.
And then we reduced that to 2 pi groups. How did you determine that we needed 2 pi groups instead of just 3? Like, what if like we would have needed all 3 pi groups? Like, how do we make that decision? Like, oh, we'll keep all 3 pi groups versus no, we just need 2.
Well, we actually just kept 1 pi group, which is we only kept pi 2. I guess if you're saying, oh, I'm sorry, you're saying it a different way. Okay. You're saying we kept, in a sense, we said this one has to matter and this one has to matter,
Yeah.
okay. This just comes down to how many unknowns are in the equation. So in this case, we introduced 2 characteristic scales. So we need 2 equations to solve for these 2 unknowns, and those 2 equations are going to come from our dimensionless groups. Why? Because our dimensionless groups are the only part of the equation that contains the 2 unknowns. So if you look back to over here, if I look at everything that I have not circled in red, does not contain our unknowns. So we need to construct 2 equations to solve for our 2 unknowns. In the next problem, we're going to have 3 unknowns, so we're going to need to find 3 pi groups to set equal to 1. So the number of pi groups that you set equal to 1 is dictated by how many characteristic values, or therefore unknowns, do you have when you try to non-dimensionalize your equation.
Okay, I see. And did we just pick values like XC, TC just because we know that those are the 2 basically like, I don't know how to describe it, like variables that are like varying throughout the problem?
Exactly.
Like no time.
The dimensionalization process works is you identify the variables in the problem, and we're going to rescale those values by some characteristic values. So in this case, there is 1 independent variable and 1 dependent variable. Ordinary differential equation, the independent variable is time, a dependent variable is height of the projectile, and so we have 2 variables, therefore we need to replace those 2 variables with 2 dimensionless variables, and in order to do that, we need to introduce 2 characteristic values, constant values, that will kind of rescale the variables in the problem.
Okay, that makes sense. Thank you.
I have a question.
Go ahead.
So when we're reducing a problem, does that mean essentially that one of the pi groups goes to 0? Is that a general like trend?
Yes.
Okay, thank you.
And the next problem we'll see is a little bit less obvious. We're going to do a problem that deals with the reaction-diffusion equation, and you could kind of choose to have this problem be reduced in one way or another, and that's where that's where the decision from the modeler comes in and says, like, okay, what do I think is small here? Is there anything that can be small? Or you might even just do both, and you say, well, I'm not really sure what's small, so I guess I could go down this way and say, maybe this one thing is small, and if this is small, it's going to lead to this set of equations. And then the other option is that this thing is small, I can reduce this whole thing down, and I'll end up with two different dimensionless equations, characteristic values that you find for each of those, and you'll have to go do experiments or simulations to figure out, like, okay, is time really set by this characteristic time scale, or is it set by this other one? And so the question of like which one you should throw out is not trivial, and usually depends on the specifics of your problem, I think, as you'll see in the next one. But yes, it does kind of involve throwing out one of the pi groups. Or if you want to think about it the other way, which I think might be more helpful, is determining what are the essential pi groups. Like, what are the dimensionless groups that I have to keep, or else my problem kind of stops being meaningful, or stops actually answering the question that I'm trying to have it answer.
Okay,
Yeah.
so this is kind of hammering this point home, but just to be clear, so the pi terms will always have either the characteristic length or time. Like, for example, we can have a pi term that just depends on G, R, and V naught. Is that something that's true, or is now that I understand? Like,
That's a good question. I think so. I think they often do. I mean,
because like the motivating factor is to set them to 1.
exactly. The whole purpose here is that we have these unknowns, and this pi group should help us solve for them. So I think so. I don't want to say always. I'm a little hesitant for that use of the word, but and I think in all the problems that I'm remembering, they do.
Okay.
Yeah. Okay. All right. Let's take like a 2-minute break, and then we'll do this next version. And then I need to let my hand uncramp. All right. And if people have questions, you can keep asking them, but we'll get back to it in about 2 minutes. Can you all see it okay?
Yes.
I know it's fine. I'm so bad with my handwriting, it's so small. I'll try to do better. It's quite small.
Yeah, so if I miss it, when you write on the big part, it's like,
Feel free to shout out if we miss it too. It's so hard for me to not write small, but I will try.
I totally agree with you that why professors don't teach this in undergrad.
I know, I kind of feel silly teaching it in like an advanced graduate course. But I didn't learn that. I didn't learn this in a class. Like, maybe others did. I kind of learned it in like ad hoc, like kind of bits and pieces in various classes.
Right.
But never someone would just say, yeah, this is what you should do. And I don't understand why. I don't understand why.
Pretty much every paper has dimension analysis, but no digit.
Yeah.
So you're
Very, very strange.
and some of the doing textbook they cover it, but they just like introduce use one-button type theory. But that's not the point. We have to teach how to use it, right?
Exactly. You have to kind of give people tools to be able to apply it. Totally agree. I don't understand it. It's never made any sense to me. That was part of the motivation for setting up this class. It's kind of realizing there's like a gap. There's this book that I think sort of does some of this stuff. It's called like All the Math We Missed. I'm just like, yeah, okay. There's been a lot of movements on this. I saw recently like I think there's like an MIT open course that was basically, it's for computer scientists. And it was kind of like all the stuff that you're using that no one ever taught you, like how to deal with GitHub and how to do like shell coding and stuff, like stuff like that. And I think there's a whole bunch of these where there's gaps, and hopefully we're trying to plug the gaps. Okay, we're gonna get back to it. Just to kind of hammer this home and to show you what happens when you have, for instance, more variables in your problem to non-dimensionalize. I want to look at a really classic equation that is a modified version of the diffusion equation that we studied in that 1D diffusion problem. So the reaction-diffusion equation, or the Kolmogorov-Borovsky Piskunov, or the KPP equation, is an incredibly well-utilized differential equation for a whole vast array of problems in fields ranging from ecology, physiology, combustion, crystallization, plasma physics. You can study the progression of a genetic trait through a population. It's a really powerful equation for creating models. And it looks like the diffusion equation, so it looks a bit like d times the second derivative of concentration with respect to space is equal to the first derivative of concentration with respect to time. So we've got the diffusion equation, all good so far, minus lambda times gamma minus c times c. So this equation is nonlinear due to the appearance of that c squared term that comes to this additional term here. Some other things that you need to know is that we have initial and boundary conditions. So our boundary conditions, the boundary conditions are the concentration at x is equal to 0 for all time, and the concentration at some distance L for all time is equal to 0. Previously, we had done this on an infinite domain, and so we were looking at kind of x is equal to 0 or x is equal to infinity. Here we're looking at a slightly different problem. It won't matter, it'll just change the math a little bit. And our initial condition is that our concentration at time 0 is equal to the initial concentration and has some sinusoidal distribution to it. So it's going to be C naught times the sine of 5 pi x over L. Okay. So this equation is not linear. The nice thing is we don't know, I haven't told you what lambda and gamma are, but based on our ability to do dimensional analysis, so let me tell you that the units of concentration are the same as before. It's going to be mass per volume. we did use dimensional analysis last time to determine what the diffusion constant was, right? And so the units of our diffusion coefficient we found to be a length squared over time. This should be pretty clear that if that's our units of concentration, then that's also the units of our initial concentration. That's pretty clear. The nice thing is I haven't told you anything about what lambda or gamma are, but based on our understanding of dimensions, we can figure them out pretty quickly. In the parentheses here, I have gamma minus c. If I'm subtracting gamma from c, then therefore gamma has to be at the same dimensions as c. So this implies that the units of gamma have to equal the units of c, otherwise you can't subtract the two. And that leaves us figuring out what lambda is. But again, we can use our understanding of how dimensionally homogeneous equations have to behave to say that, well, I'm subtracting the derivative of concentration with respect to time from all this junk on the right-hand side, lambda times blah, blah, blah. And so therefore, I would say that the dimensions of gamma, oops, that's not supposed to be gamma, of lambda times gamma minus c times c has to be equal to the dimensions of dc dt. Is that clear? Otherwise, you can't subtract the two. They have to be at the same dimensions. We know all the dimensions of c and gamma, their concentration, so therefore, I will leave this. This is like a nice exercise you should go and do on your own. Figure out, convince yourself that the units of lambda are length cubed per mass time. So you don't even need to know. I don't know what it, like you could be, if you're like an applied mathematician who's not working in this field, but is just trying to look at this equation and figure out what's going on, you can really quickly figure out what all the dimensions are just by making sure your equation is dimensionally homogeneous. Okay. So now what do? Well, we do the same thing we did before. We say, in this equation, I have, let's do this here.
What's inside the sine term in the initial condition? Is that
Sine of 5 pi times the dimensionless length, x over L. L is some length in the problem. We haven't specified what it is. Oh, what am I doing now? I'm just change your variables. Okay, so here we have three variables. We have x and t are our two independent variables, and concentration is our dependent variable. So we're going to make three changes. So we're going to say that x is some characteristic x times u. T is some characteristic time times s. This is the exact same thing we did before. I'm just picking the variable the same. And my concentration is going to be some characteristic concentration times v. Take, say, 3 minutes, do the chain rule, and see if you can insert this change of variable into our original equation to get a dimensionless equation. You don't have to worry about rearranging everything perfectly yet. Just see if you can apply the chain rule properly. Insert all of these variables into our equation. All right, just for the sake of time, so we can get through this. Here's what I got. So hopefully you got something similar. You might have maybe terms moving around. Maybe you already started the grouping things dimensionlessly. But spatial, same thing's going to happen here. You're going to get a 1 over xc squared because of your chain rule for substituting in the second derivative of space. You're going to have 1 over tc appearing here. And then this just comes from the insertion of your concentration and pulling it out since it's a constant. And this part's pretty straightforward. So hopefully you got something that looks like this. Here's the part that is, like I said before, more of an art than a science. You just need to kind of move things around until you get some dimensionless groups appearing that look nice to work with. So what does that mean? Well, it means that we know that d is a length squared per time. So I kind of need I have a length squared in the denominator. I kind of need a time on the numerator to make that dimensionless, so I can move this thing over here. I can move the cc and cancel out on both sides. So let's go through this process. And then we'll do it again. So my first term should be something like this. And that's going to be timed as my second derivative. I cancel out. I move the TC over to the left-hand side. I move the characteristic concentration to the right-hand side. So this term got canceled out through that process. So I end up with just the derivative of v with respect to s. And then just following through with what I did for diffusion, I get something like lambda times Tc, Cc, gamma over Cc. Now gamma we said was concentration, so dividing it by the characteristic concentration makes sense. Actually, hold on, move this over. Times V gamma over Cc minus V. So this should hopefully look to you, this is dimensionless. Clearly dimensionless, clearly dimensionless. This one's a little less obvious. Concentration time, this thing was length cubed per, this is kind of like inverse concentration times time, right? So I need to multiply that by concentration and time to cancel it out, which is exactly what I have. And this is pretty clear, concentration over concentration. We need to do our boundary conditions. We're basically, for S, we're going to be dividing through by XC and TC, our characteristic length and time scales. We're essentially dividing our initial conditions and boundary conditions dividing through by XC and TC. So when we do that, we end up with that my concentration at 0 and S equals my concentration at L over XC. Remember, we're dividing through by XC and TC and S. And that should equal 0. So now this is dimensionless. So dimensionless, and this was by default dimensionless. These are two boundary conditions, and my initial condition is that V times U, sorry, V of U at 0. I'm dividing through by my characteristic value, so it's C by C naught, sorry, C by C naught by the characteristic concentration times the sine of 5 pi times XC U over L. So again, we are essentially, to get our initial boundary conditions, we essentially divide through our characteristic scales, 3 of them. All right, so that gives us 5 pi groups. Let's find them. Pi 1. Oops. Pi 1. Over here, this is pi 2. Here's pi 3. And let's see, we have 2 more. This is pi 4. And this last one here is pi 5. You might say, hey, what about the one inside the sine term? That should be pi 6. I have XC over L. But pi 6 would actually be 1 over pi 4. So we don't need to have that one. So we can just leave it as 1 over pi 4. Yep.
Yeah, and again, choosing which one that we would make a pi term, that's kind of arbitrary.
Yeah, like you could call that pi 4 and the other one 1 over pi 4. Doesn't matter.
Okay.
Yep. Okay, so there's 2 things I want to say here. One is we apply the first rule kind of before we were trying to think about the physics of the problem. Or I shouldn't say before we think about the physics. No matter what reduced problem we choose or what limit we're interested in, it's essential for us to keep the boundary and initial conditions. So the first thing we can do right now is immediately apply rule 1, which is that pi 4 and pi 5 have to equal 1. So if we apply rule 1, we find that pi 4, which is L over XC, equals 1. And pi 5 is that C naught over CC equals 1. And therefore, we've already found that our characteristic length scale in the problem is whatever that L is that we're interested in. So that's going to be set by like, oh, the domain over which we're studying is diffusion. And the characteristic concentration of the problem is pretty clearly just the initial concentration. That's kind of the scale that we're interested in. This gets to your question of like, What if I chose the other one as pi 4? No matter which one you chose for pi 4, you're going to get xc is equal to L. Doesn't matter. So we've already got 2 of them. Right. Remember, our goal is we have to set 3 pi groups equal to 1. So that way we can find the 3 characteristic values. We found 2 pi groups in our initial and boundary conditions, and that's always where we start. We set them equal to 1. So we have now our two of the 3, our characteristic length and characteristic concentration are set because by applying the boundary conditions. Rule two, which is the reduced problem, or another way to think of it is, what is small? What's the small thing that I can try to neglect? And here's where we have a choice. There are 2, so I'm going to come down here and rewrite this down below. So let's use purple here. So we have that pi 1 times the second derivative concentration minus pi 2 v pi 3 minus v. So we have 3 to choose from. Notice in this problem, we can't automatically assume that we have to keep this one. Getting rid of this thing is one limit of the problem. It's the limit of weak diffusion. So this is my diffusion term, right? So I have diffusion by some characteristic diffusion time scale. If I say that pi 1 is equal to 0, and I can arrive at a reduced problem here, that would be the limit of a weakly diffusive process. So I have some dynamics happening right here. The nonlinearity is really important. The diffusion is not. Maybe the time scale that I'm really interested in is super small. Diffusion has a really long time scale because the domain that I'm interested in is really long. So in that case, I'm looking at a weakly diffusive process. The other one here has to do with the nonlinearity. That nonlinearity comes from this product here. The only way to get rid of the nonlinearity is to throw out pi 2 here. If I throw out pi 2, I get the weakly nonlinear form of the reaction diffusion equation. The weakly nonlinear form basically says, it's kind of diffusion. Maybe the nonlinearity matters a little bit. We'd like to be able to account for how much it matters. But the reduced problem would be just the diffusion problem. And then we can build back in the nonlinearity as we need to. I don't really have a physical intuition about what setting this would kind of do for us. Setting this equal to throwing this out, because you would still have a nonlinear problem that's also involving diffusion. So maybe there's a limit there that I'm just not aware of, but I'm thinking of the pi 1 and pi 2 as kind of being the crucial 2 cases. Yep, question here.
I mean, also like pi 3 won't help us solve for TC, right?
That's probably a better way to say it. Yeah, thank you. That's actually I guess that's a smarter way to evaluate it. What we're trying to do is figure out TC, and only 2 pi groups have TC, and those represent 2 kind of different ends of the spectrum. So the question is, what's the problem we're interested in? So we can kind of first say, well, let's look at the let's set this equal to 0 and look at the weak nonlinear problem. And if we set that equal to 0, that means we have to set pi 1 equal to 1. Oops. Pi 1 is d times 2c over xc squared. And it should come as no surprise. We know what xc is. It should come as no surprise that my dimensionless ratio here is going to be, oops, my time scale is essentially L squared over D. I say this should come as no surprise because the characteristic time scale in any diffusion problem is a length squared over your diffusion coefficient. And in this case, we basically threw out the nonlinear term, got back to a diffusion problem, and there we go. So that's one of the limiting cases. The other limiting case, pick a different color for it. Let's go with pink. Is the case of weak diffusion. So if the problem you're interested in, like I said before, has a really long length scale, then diffusion is going to happen really slowly compared to the other parts of your problem. So maybe the nonlinearity is really important at all times, and the diffusion is really not important immediately. In the weak diffusion case, let's see here, and then I'll go back and write both of these equations out with the new terms inserted. In this case, I'm setting pi 2, which is lambda TC CC equal to 1, and therefore my characteristic time scale here now becomes 1 over C naught lambda. So my time scale now is not dictated at all by my diffusion coefficient. It's dictated by the magnitude of lambda, which is going to scale the nonlinearity in my problem. So how fast is that nonlinear term affecting the rate of change of concentration in my system? So this leads to two very different problems. So here I said that I can, let's continue over here. Using this equation, I can write that we set pi 1 equal to 1. So my dimensionless equation looks like this. I've replaced pi 2 with epsilon because I said it's my small parameter in the case of weak nonlinearity. And by inserting the other characteristic values into my initial conditions, I get something like V0 in S is equal to V1 in S is equal to 0. I'm running out of time, I apologize, but you can hopefully verify these initial boundary conditions. Remember, all the terms that maybe we had before, they're disappearing. They're disappearing because we set them equal to 1. We explicitly set them equal to 1. So now here is the system of equations I would solve for the weakly nonlinear reaction diffusion equation. And I can do the exact same thing. All I'm doing, just to recall, all I'm doing is inserting my characteristic values, CC, TC, and XC, back into my dimensionless equation. And I have two different problems here. The second one is in the limit of weak diffusion. I would get that my small parameter is now epsilon that multiplies the diffusion. Now, some of you might be saying, hey, wait a minute, last time you said that throwing out the derivatives was a problem, and that's why we kind of didn't want to throw away pi 1 in the projectile problem. How come we're doing it here? And I want to just point yourself to your attention to a subtle but really important distinction between these two problems. So we took the reaction diffusion equation, we non-dimensionalized it, and we found that there was kind of two ways you can non-dimensionalize it, depending on the physics of your problem. Either the nonlinearity is small or the diffusion is small. Here, epsilon, my small parameter, multiplies the nonlinear term. If epsilon is taken to exactly 0, I end up with the diffusion equation. Not too bad. Here, my epsilon, my small parameter, multiplies this derivative term here. Not only does it multiply a derivative term, it multiplies the highest order derivative in my equation. This is a significantly harder problem to solve because when we take the reduced problem of there being no diffusion whatsoever, we lose the second derivative and we lose the ability to apply two boundary conditions. Now that doesn't mean we can't solve the problem. It means that solving the problem is a lot harder. And when we get into approximating these solutions using small parameters, we're going to build everything off of epsilon. We have an epsilon that's going to be small, and we're going to say, how do we approximate our solution as epsilon gets a little bit bigger than 0, but close to 0. And what we'll find is, this is pretty straightforward. And this one's not. And a lot of the problems that you encounter, for me, I work on thin structures where we're interested in like the deformations of thin sheets. These involve fourth order derivatives in space. And the small parameter in that problem multiplies the fourth order derivative. It makes solving them incredibly hard. It makes even numerically solving them incredibly hard because these are what's called stiff equations. These are equations in which approximating them or solving them, it's so sensitive that fourth order or second order derivative being multiplied by a small number leads to a lot of numerical challenges in there. So we started with a problem on reaction diffusion, identified two limiting cases, one where the nonlinearity is weak, one where the diffusion is weak. And we actually found out that, or if you take my word for it, that the scale in solving these problems is really different. This is not too bad. This one is quite challenging. And we'll investigate both of these types of equations going forward. But the key takeaway here is we figured out how to non-dimensionalize equations, and the end result was these epsilon terms. I'm going to give you all a homework assignment to work through. I'll send it out after this class, so that way you're comfortable and you can quickly non-dimensionalize these equations. Because from what we're going to do next is going to be using epsilon and small parameters to start approximating equations. All right, I have office hours in like 15 minutes, so if you want, just jump on Zoom and I'll chat with you then. Thanks.
Just a short question. Isn't the plus on the right-hand side should be negative?
Should it be negative? It might should be negative. Yeah, why is it? Yeah, I think you're right, but I think I have it in my notes wrong. But I think it's negative. Yeah, thank you. I don't know why I have that wrong. Thanks.
I have a question. Would it be possible to just zoom in on the pi 4 and pi 5 terms? I couldn't really. Oh, thank you. Yeah.
Sorry about that. I'll upload this to the website in the next couple of hours. So I know that my handwriting is small. Thanks for bearing with me. I'll have this posted online as a PDF that you can check out in the video whenever possible. All right, thanks everyone.